recording. Somebody had a question? Oh yes, the chapters would be whatever we started out with up to chapter 20. Yeah, up to chapter 20. Basically what's covered in homework up to homework, what is it? Homework 20. Is that right? Yeah. So it will be over those. And today I want to kind of like review a little bit, but actually emphasize what is important for our daily life. Because after all, we all use a lot of circuits and a lot of devices and things. And the thing that we really need is to recognize electric hazards. So I downloaded from my other course some slides in order to emphasize this electrical hazard thing. All right. Oh, before I go on, what was it? 17? Somebody had a question on 17 is, I think yeah, it's part of what was chapter 17 about? I get all confused with so many different lectures. 17 was on Coulomb law? No? Well, yeah, you figure it out. I don't remember. Yes, before I continue, I just want to again remind people that the test number 1 is October 6th, Wednesday at 5 p.m. to 6:15. Oh yes, linear superposition of waves. It's the simple aspect of it, not the full chapter 17, but just the linear superposition of waves. For test number 1, it will be live in person. I still have no confirmation. I was told it was MR3, Marshak 3, but whoever is the registrar involved was on holiday or something and did not answer. So hopefully I will be able to answer it by Wednesday. All right. Now for the exam, you have your own laptop. You have all of whatever is your PowerPoint and whatever notes you have, and the text. It's all with you. So in a way, it's like an open book. But what the proctor does, and there will be proctor at that room, what the proctor does is to make sure that you don't chat with one another and pass one sheet with whatever formulas to the other sheet and say, hey, this is the formula you should use when you have this question. It is to be one where you are silent and no talking around. I will be live online with chat so that if you have some questions about, oh, what does this mean? You can chat with me. I will not be there personally, but I will be online chat. So you mute it's all on Blackboard. It's not on Wiley Plus, it's on Blackboard. You mute your microphones and you can ask me questions. The proctor wouldn't know because after all, it is I who set up the exam, all right? So but you have to be live, because if you are not live, then as far as CUNY First is concerned, you're dead. Well, I don't want to use that severe term, but you have to be live and you have to make sure that you have the vaccination proof. Okay? Now, electric hazards. In our household circuits, we can have things that draw 10 amps. We can have things that draw only 0.1 amp, 100 milliamp. But nonetheless, they can be dangerous if there is a short somewhere in your circuit. And household voltage can be lethal if you are wet. For us in America, the Con Edison supplies the voltage at 110 volts. It's not as lethal as elsewhere in Europe. In Europe, if you were to encounter the same kind of short and you put your wet fingers into the socket and it is 240 volts, bye-bye. It's not, you're not going to survive. At least, I don't know. I wouldn't want to advise you to test it. But over here, if you accidentally, you just go through and then you sort of, get shaken off. So it is not as lethal. That was the decision by Edison to lower the voltage when it comes to the house, not at 240 volts, but at 110 volts. All right. But nonetheless, be careful. And a person that becomes receive a shock is because you become part of the circuit. For whatever reason, you become part of the circuit. And then, of course, the current will flow into you and cause you an issue because your body resistance is not that high. And the current that now flows through here, because it is 120 volts, is big. And it will give you a shock. And all this cartoon says, yikes. But I don't know if you will say yikes, but you may say, ouch, whatever. Now, faulty wiring can be hazardous, and now we better be sure that the electrical work is done by a professional. If you take, for example, the microwave oven, if everything is working well, and you use just a two-prong plug, you know what I mean by two-prong plug, right? If you use a two-prong plug, this diagram shows you that indeed it is a circuit where Con Edison provides the input voltage, whether it is 110 volts or 120 volts. It now comes in and it goes through whatever is the internal resistance of this microwave oven, and it goes back out, and it's been insulated so that even when you put your hand on top of the microwave oven, you're okay, because the circuit has been done. The manufacturer, when they made the microwave oven, they've already made it such that there is no direct current, touch of the wire inside to the outside box. However, if for some reason, because of it being used old enough, or when it was wired, there was some defective wiring, and if one of those wires inside the microwave oven were to now touch the outside box, if one of the wires inside the microwave oven were to touch this box, outside box itself, then the current or the electrons now say, gee, I have a new way out. I can in fact go out over here and go to the ground, because the electrons, they just want to run away. They have been sent in, they want to run away. And they say, hey, I have now a new way, which is to come through you to go to the ground. Well, what happens is, indeed, it went through you, and what you got was a shock. But if you now, when you install and you plug it in, your microwave oven or your refrigerator or your electric oven, if they come with a three-prong plug, then there is what they call a ground. And this ground provides now a route, an alternate route. If in case there's any kind of a short where the inside wire now kind of like touches the outside box, well, the ground, the electrons now say, there's an easy way. Just go by this, go into the ground. So you will not then get the shock. So it is important to be sure that you install and make sure that for these appliances that it should be a 3-prong plug. And for the electricians, I'm not an electrician, they know what is black wire, white wire, what's neutral, what is hot, and so on. Well, that's for engineers. It's not for you, not for me. But the advice is make sure that it is in with a 3-prong plug. And now, this is just to review what you have already learned. When you have a potential difference of whatever is the potential V, the work done when the charge Q moves through a potential difference of potential difference V is Q times V. I'm sort of like helping to review it. The power that is consumed by this during this is the amount of work done per unit time. That's the power. But if the work done is QV, then the power is Q over T times V, but Q over T is what we call current, I. So therefore, the fundamental formula for power consumed is P equal to IV. Right? I mean, that is the most key, simple formula that everyone should be familiar with. And when you buy a refrigerator, when you buy an air conditioner, they will tell you, oh, this air conditioner is rated at or designed for a power rating of 1500 watts, or it could be 2500 watts. If it is more powerful, you of course you pay more for a air conditioner that is 2500 watts, or and so on. So they tell you what is the rating for the power usage, and they mean for you that it is to be used within the United States where the voltage is 120 volts. And when they tell it to you that way, the actual current that will flow through, or you use this formula. They don't tell you, oh, what is the current that will flow? Because it really depends on what's the voltage that you put in. And they don't tell you what's the resistance of this air conditioner, resistance of this microwave oven, or resistance of this refrigerator. They only tell you what is the power, and that this rating is for use in America, and so the voltage is 120 volts. And the unit is watt. We have already looked at it. And now for all of these devices, there is this Ohmic law, which says that the actual current that flows inside this device, the actual current depends on your voltage and your resistance. The current that flows is your voltage divided by your resistance. But since they didn't tell you the resistance, they only told you the P and the V, you can actually then work out that P is actually I squared R. If they didn't tell you the current, didn't tell you the resistance, nor did they tell you the current, but you know it in terms of the voltage, then P is V squared over R. And therefore, if they say if you say, I bought this air conditioner and it is rated at 2500 watts, and I know I'm using it in America where V is 120 volts, therefore I can work out what is the resistance. Or if I know the resistance and I know the voltage, then I know what is the power used. So if you, for example, have a hairdryer and you bring your hairdryer because you're going on a trip to Paris or to Amsterdam, Netherlands, you then will bring your hairdryer that already has a resistance that doesn't change. But when you go overseas, the voltage is double what is in this country. Therefore, the power used on the hairdryer now is 4 times. If it was rated at 1500 watts in this country, you brought the same hairdryer to be used in Europe, and you plug it in to the circuit over there, then it will be drawing 4 times. It will be 6,000 watts because the resistance is the same, but the voltage increased by double, therefore it is 4 times. And what happens is your hairdryer burns out. And so when you're traveling, another advice which is important for us, when you travel and you bring your hairdryer, don't plug it in your hotel suite, but plug it in the bathroom, because in all the hotels, at least the normal, hotels, in the bathroom, they have a special plug for US, because that they make sure is at 110 volts or 120 volts. It's safe to use that plug over there, but don't plug it into in your room, in your, where the dresser is and so on. It's good to know this. If not, you will be in trouble when you are overseas. You brought your hairdryer and then you say, ooh, I really burned it out. Okay? And now I just want to finish with this issue of Edison, how he was so considerate. As I mentioned earlier, when you have a power plant, they want to generate power. Oh, the kind of power that you generate is so many megawatts, or in fact, it could be even almost gigawatts. They really generate a lot of power, and now they want to transmit down to New York City, and this could be in Niagara Falls. Well, if they transmit, then the question is, this transmission line itself has a resistance, right? After all, you have to have a wire to connect. And this resistance, this wire is not 3 feet, 10 feet, 20 feet. It is 400 miles, 500 miles. I don't know how far it is from Niagara Falls to New York City. Must be 300-400 miles, right? And so for the industry, the power industry, they want to reduce the resistance, because after all, it is, the longer it is, the bigger is the resistance. The bigger the resistance, the more is the power loss. Okay, so what they do is they say, well, I now know, I need to know this. You remember this formula? That I need to know that the resistance, the notation here is, we used to use L, but the other book, Pearson, uses curly L, but don't be upset or be so fussy. This is the length of the wire, and this A is the cross section of the wire. And this is resistivity. And for a given material like aluminum or like copper, the engineers will tell you the resistivity is blah, blah, blah. I don't even know, but the electricians, the engineers, they know. And then they say, I have already chosen copper, so rho is fixed for me. Now, our mission is to reduce this resistance. Therefore, we have to now make sure that this A is thick, not thin. And we then have to just simply say, okay, I've chosen the best resistivity, and I now will be able to estimate, given that it is so many 100 miles, what is the total resistance of this wire? All right? And, well, that's just algebra. And the power now lost, the power that is lost through this transmission wire is I squared times R. Is I squared times R. And I now need to re-express it as V squared over R all right? And what I need to do now is to say, I want to have this resist power loss. Oh no, that power loss is I squared R. What matters is the current that flows, I squared R. And I want to now reduce that. I want to know what is my power loss. And you will be able to figure out if I move it up, if I transform it to make it to be high voltage, yeah, oh, right. I'm staring at this. If I raise the voltage, the power is fixed. That's my plant. My plant has so many megawatts. If I raise this voltage, my current becomes smaller and smaller. You got it? I can't do anything about this. I've already done the best I can. I chose copper and I have chosen the thickness of the wire. What I can do is to raise the voltage from this side. I raise it from whatever is the one I produced it at, 12,000. I raise it to 240,000. Nowadays, it's not 240,000. They raise it to 675,000 volts. So if I raise this V to a very, very high voltage, the current becomes smaller. And therefore, I'm minimizing the loss of my power that I have supplied. And so they say, bring it up as high, 675,000 volts. But then when it comes to New York City, you cannot supply my home, your home at 675,000. So what they do is they step it down. You know, there are transformers that step it down from 675,000 to 240,000, down to 12,000, down to 7,000, down to 240 volts. And Edison, since he was living in America, he says we should lower it down to 120 volts. The rest of the world, they say, it costs too much. Because each time you have a transformer, there's economic cost involved. So the rest of the world, they just say, it's okay. All of the people are very conscious of not sticking your wet finger into the socket directly. So they live with 240 volts. But Edison made sure that when it comes in our home in America, everywhere it is at 120 volts for our safety. Are you able to see the overall picture here? Your power is the method of, however they produce it. And we will learn about that when we learn more about Faraday's, induction law. So, but what is important is they raise this, they step it up by transformer to 675,000 volts. Then the current is small, then the loss is I squared R. And when it comes down on this side, you step it down and step it down and step it down. And for us, it has been stepped down to 120 volts. All right, so overall summary. Oh, they raise the voltage in order for this transmission not to lose money. After all, they spend a lot of money generating this electricity. But if, let's say, they have generated 100 megawatts, but if 50 megawatts is lost on the transmission over 400 miles, then they can only earn based upon, half of it. So what the power industry does is they want to be sure that it is at a very, that the loss is not big, that this loss is not big, because you have minimized this current I. And how do they minimize it? They step it up, step it up, step it up. Step up the V, big, 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 big. Then I, of course, gets smaller, smaller, smaller. All right? Is that clear? I mean, the concept, is that clear? Yeah, I mean, the electricians will have to work with it, the actual numbers and so on, but the concept is that you want to now minimize the loss. Okay, all right. So now this is an overall summary. The big Ohm's law, that whatever is the voltage, the current that flows out of it is dependent on your resistance, V equal to IR, and the power that this thing consumes is I times V. And you can, of course, use this to write the power consumed is I squared R. The power consumed by your microwave oven is the resistance inside your microwave oven times the current that flows inside. Well, so whatever is the power rated at 1500 watts, and the resistance by design by the factory is so many ohms, then the current is 10 amps. The current is, I don't know, what is the actual current inside the microwave oven. And you can then re-express it by algebra, that the power that is rated at depends on, I mean, it's already rated at, and you are using it at, in United States, voltage is 120 volts, then it is another way of saying the resistance is blah, blah, blah. Because the resistance is V squared over power, and you know the voltage, you know the rating, therefore you say, oh, the resistance is 7.5 ohms. All right. And then there's this thing about the resistivity and the length. And then the summary of chapter 20 is resistors in series, they just add. You have three of them together, then the total resistance is R1 plus R2 plus R3. If they're in parallel, then it is the reciprocal that add. 1 over R1 plus 1 over R2 plus 1 over R3. That's because when they're in parallel, the current splits into I1, I2, I3, but the total I is still dependent on your voltage V. We already saw that with your lighting, holiday lighting. You know, you want to have 100 bulbs on your lighting thing, and you don't want any one bulb to burn out to cause the entire line to be dead. So you have parallel, that these lights are plugged in parallel, so that if one of them goes out, that's okay, the rest are still lighted up. And we also have capacitors. Now for capacitors, if they are in parallel, then they add. If I have a battery and I have another battery but in parallel, then the total capacitance, which is Q equal to C times V, the total capacitance is now, you just add them because the total charge is now bigger. But if it is in series, then it is the reciprocal which is added. So this is just for the simple application involving capacitors. All right. Any questions? I just went through basically a review of what we have been dealing with. No questions? All right, let me now go here and no questions so far. Yes, good. But do ask questions because that, oh, let me put up the other guy. You see it now? Yeah, right, okay. We now come to chapter 21, it will not be on this test number 1, but it does not mean that therefore you can forget about magnetic forces, because then it will be a very important part of test number 2. And in a certain way, there's something more subtle or more sophisticated with magnetic forces than it is with electric forces. Have you heard of the difference in the expression, he has an electric personality versus he has a magnetic personality? What's the difference? When you say a certain person has a magnetic personality, I guess you have not been... this won't be on exam 1, but you need to learn this, because that is one of the more, let's say, interesting aspect of electromagnetism. Electric forces are sort of very direct. I either hate you, or I either like you or hate you. I just, the forces are straight. Okay? But when magnetic, it's more subtle. Yes? And actually, therefore, you have to be more careful. But it pulls you to them in a slightly different way. And that's what we need to focus on. And you begin to learn something about what you call the right-hand rule. But anyway, so this now, for magnetic force, we need to first understand this thing called a compass. Yes, this is an example of a compass. It is a compass that is what we call the North Pole and the South Pole. Do you use a compass at all? Does anybody use a compass these days? Yeah, never. Nowadays, all you do is you go GPS, and then GPS says go north. When I turn on my GPS and they says turn northwest, and I say, wait a minute, I don't even know where is north, so what do I do? Only after a while it will then say turn left, turn right. But when my GPS starts, it will just say go northeast. And I really would like to say to this GPS, I say, wait a minute, how do I know which side is north, which side is south? But in the old days, it is very important to have a compass, because otherwise you wouldn't know where to go, right? And the reason why a compass is important for us is because the Earth is also a magnet. We don't realize it, we don't recognize it, but the Earth itself is a magnet. And the Earth has a magnetic field around it, which when, what's his name, Friedrich Gauss was working on it, he already figured it out. And it's like a third of a Gauss. The Earth, that magnetic field on Earth, when you carry your compass, that the magnetic field that we detect on Earth is about a third of a Gauss. But later we'll see that the metric system, the System International, they don't honor Gauss. Instead, they honor Tesla. Have you heard of the name Tesla? Oh, you're not rich enough to, huh? You've heard of Tesla, right? Yeah. Tesla is now made famous by Elon Musk, right? Isn't it Elon Musk who make Tesla famous? Yeah. But anyway, from a purely theorist point of view, it's actually Gauss who should have been given the honor, but what are we to say? It's the, whatever this system, international, those people, they decided. Anyway, so here is this magnet. And the magnets also have this sort of property that like poles, namely I have one magnet, one compass, and they both are pointing this way, let's say, then if I have two such magnets, they repel each other. But if I have one magnet, one compass that is oriented this way, and the other one oriented opposite way, they attract. All right, so they call it like poles repel, unlike poles attract. But this is the sort of like this does not fully introduce the aspect of magnetic field. This only like if you have two compasses, you discover that, oh, some of them like each other, some of them don't like each other. It all depends on your orientation. What is more subtle, we will come up just a minute, okay? But this is just so that you can see that you can have two like poles, they will repel, opposite poles attract, and we will see why. Because surrounding a magnet, there is a magnetic field. Just like a charge, Q. Oh, we already spent 2 or 3 chapters in understanding that a source, charge Q, it will be the source of an electric field, and this electric field points away from the positive charge source, or it points towards the positive, negative charge, if it is negative charge, and then you will be affected by my electric field because you also have a charge. You call it your own charge, capital Q or little q. And your little q, if you have your little q and your little q is also positive, the force on you is QE. Whatever is the electric field, it will now affect you because you have your charge little q. All right, so that is this electric field, that every source is the source of an electric field radiating outward from it, and this electric field will now impact on you if you are charged. If you are not charged, you will say, what's the big deal? But if you are charged, you say, ooh, somebody is pushing me, and he's pushing me away because the source was positive and I am also positive charge. But if the source is positive and I am negative charge, then the force is Q times E. But since my Q is negative, I am now pointing towards you. So that was the way the electric field language came to be. Now there's also a similar kind of language, but it is for a magnet, that there is a magnetic field. And now, if I have a magnet and it is one end of it is north, one end of it is south, the magnetic field will go from north to the south. It will go from north to the south, and it will go north all the way and south coming all the way. In other words, it will be a sort of like these electric fields are not, the magnetic fields are not like the electric fields. The electric fields just radiate radially, just go all over. But this magnetic field of a compass, of a magnetic, they call it dipole. For a magnetic dipole, the magnetic fields go around. All right. And I think the next picture will have it. Yeah. The magnetic field lines actually go all around. And there are some that go all the way up and come back, all the way up and come back. And there are some that go all the way to infinity and come in from infinity. That is the magnetic field. Of course, the magnetic field gets weaker as you go further and further away. But the magnetic field, unlike the electric field is just radiating radially, the magnetic field curves. All right. And if you were in a lab, you can actually map this electric field, because you can put all these, there's your magnet, and then you have a glass over it. And then if you spray some these dust, not dust, I'm not a experimentalist, but if you have some metallic stuff, if you put some metallic stuff on top of this plate, then the metallic stuff now would be arranged, would cluster in this direction, which maps out your magnetic field. All right. In other words, there's a way of actually visually in a lab show you the magnetic field lines. But since you're not the engineers, we don't have to. And or maybe in one of the labs you will see it actually, perhaps. And if you now have a magnetic, they call it like a ring. If I have a magnetic ring where I basically bend this magnet into like a donut, then the magnetic field lines from the North Pole will shoot across to South Pole, and this would be the set of magnetic field lines. All right, so this now gives you a sense of the difference between electric field and magnetic field, that the magnetic field are not so direct. Magnetic field sort of curves around. And here now is the interesting fact, which most people may not recognize or realize. We call this the North Magnetic Pole. After all, you notice the compass, it was pointing north, right? And the direction up was north. And so you say, this is the North Magnetic Pole. But do you realize, for this to be so, the Earth itself, this is the South Pole of the Earth magnet. You are pointing north, but this actually, the Earth magnet is the south, is the south end of the Earth's magnet. And the magnetic field lines go from the North Pole, go to the South Pole of the magnet. And these are the magnetic field lines. And here I just want to mention something. I don't know how many. In China, the word for compass is the needle that points south is the compass. The needle that points south. You know why? I mean, it all has to do with geography. Because from China, in order to go around to Italy, to Europe, you have to go down south in order to go that way. And so they use the compass to be one which is south pointing needle, which is what we call compass, and they use that for navigation, right? But those are all just okay. Now, to compare with the electric field, we know, and I was just already doing it, we know that if I have two sources, one is positive, one is negative, that we know that this is a source of electric field away from it. And that is, if I have a charge which is positive, the force will be away. But if I have a negative charge, the force on this charge due to the electric field from here is this way. So this is just what the book already showed, right? Because F is equal to Q times E, and it depends on the sign. Whether it is a positive charge, then the force is in the same direction as E. If it's negative charge, the force is opposite to it. Now, we want to now begin to formulate the law of force. We already showed for electric field, it's so easy. F is Q times E. Now we want to come to what is the law of force for magnetic field. When I have a charge and I'm in a magnetic field, what is the force? Well, there are certain conditions, and they are very important conditions. If the charge is not moving, there is no force. You can have a very strong, intensive magnetic field, but I have zero velocity. I'll say, quel le problème? I have no force on me. I have to be moving in order for me to feel a force. For the electric, you were not moving. You had a charge, and I put an electric field in your presence. You have a charge. You will start moving because there's a force on you. For the magnetic field, I have no charge. And even if I have a charge, I'm not moving. No force. But even if I'm moving, the velocity must have a certain component perpendicular. I mean, this is saying it in ordinary language, but it's easier to understand. When you, I thought I inserted a formula for it. It's easier to understand, but we'll come to again this slide back again. It says that if I have the magnetic field here and I'm moving, but I'm moving parallel to the magnetic field, there's no force. But if this is the magnetic field and I'm moving perpendicular to the magnetic field, yeah, there's a force. But which direction is the force? It's neither this way nor this way. Instead, it is upward. So you can see it's a very, you can say confusing, but very subtle way. I am moving through this part of the ocean, and there's a certain magnetic field. Then I find that there's a force is veering me away from the direction I'm going. You see it? I was going in this direction, and that happens to magnetic field, then I get to be veered off. I was moving, and now there's a force on me sideways. And the direction, there is something called the right-hand rule, which we will come to. And for this case, I am moving perpendicular to the magnetic field, and the force is upward, V cross B. And for this case, it was moving which way? I guess this direction. There again is also a force upward. So here is now the right-hand rule. And I want to quickly write down the mathematical expression. And this is the way you can realize it. It's right-hand rule. They call it right-hand rule number 1. But anyway, this is the right-hand rule for the force on a charge, which whatever is the charge Q, and it is V cross B. And here is where you have to be good with the right hand. If you have your right hand, your hand has to be such that V is in the direction of your forefingers. Well, they have it differently, but I do it this way. I don't do it the way they have it. I do it this way. I don't know how. You know, here is my hand, right? My right hand. I first let my palm, my hand, my palm, point in the direction of V. Whatever's V, because I was going this way, so my V is this direction. And then I will now wrap my hand in the direction of the magnetic field. So if I'm going this way and the magnetic field is this way, then my thumb will show me which way is the force. Are you able to see what I'm doing? You see, you have to wave your hand, right? You wave your fingers, and first you point your whole palm in the direction of V, because you're trying to get V, right? So you say, oh, I was going in this direction, and there was a magnetic field, and the magnetic field is to my left. Then I will say, okay, I will curve my hand in the direction of the magnetic field. And if I'm able to do that, then my thumb gives me the direction of the force. You got it? And so this is the right hand rule. And now, if, for example, I went like this and the magnetic field is not this way, but the other way, and then I will say, Monsieur, right, let me again say that. My palm is in the direction of where I'm going. I'm going this way. But now, if your magnetic field is opposite to my, let's say this is my right hand, to my right of this hand, I cannot bend my finger that way. But what I can do is I turn my finger this way. Then this is still pointing in the direction of V, but now I can curve my hand and my four fingers will point in the direction of the magnetic field, and my thumb is now downward. Do you see what I'm doing? When it's live, I can show you, but when it is not live, it's hard for me to show you.
Hi,
Are you following? What?
So you're saying if you point your thumb down, that's the direction of the force?
Yeah, the thumb would be the direction of the force. If you are able to bend your hand in the direction of the magnetic field, right? Let's say you stretch out your right hand, and then you say, "Hey, I can now bend my hand from the direction of V into the magnetic field, and the thumb then is upward." But if I say, "But you told me, you show me that your magnetic field is the other side. I cannot bend my hand backwards." You follow what I'm doing? I cannot, I refuse. But what I can do is, of course, go like this. And then you see, I still am pointing in the direction of V, but now I can curve into the magnetic field, and my thumb now is downward. I didn't catch the your chat. Did somebody, can you say it out loud? Somebody had a chat. What was it? No.
So if it is the velocity of a charge is to the right of the magnetic field, the force is downward.
Yeah, namely, this is my velocity, and now it is, to this side, and I say, gee, I cannot do it. What do? I turn my hand so my thumb is downward. Then I say, oh yeah, no problem. Yeah, I was going in this direction, and now your magnetic field is the backside. No big deal. My thumb is downward, therefore the force on me is downward. That's what this V cross B is showing me. You got it? So this is the right hand rule, and it's important to have your right hand. I don't know how you would do it with the left hand, and if you do it, you have to invent your own, sense. All right.
Professor,
so
B
okay.
is the magnetic field, right?
What? Louder.
B is the magnetic field, right?
Yeah, B is the magnetic field, right? And it has a sense of direction. And if I already started out going this way, and your magnetic field is a convenient, I can just bend my finger this way to point in your direction, then I know the force on me is upward. But if you now say the velocity is this way, but your magnetic field is on the other side of it, and I say, ooh, I cannot do it. What do? I turn my thumb down, and then I say, yeah, I can now do it. V is still in my original direction, but my magnetic field, because you changed the direction, the magnetic field is this way. then my thumb is pointing to the direction of the magnetic, to the force that is acting on me.
Professor, there is a question.
Yeah.
What if the velocity is to the left? Is force is to the left? Does that mean force
No,
to the left?
no. The force is your thumb. Whatever the thumb shows, that's your force. But first you have to line up your hand in the direction of the velocity. All right. Let's say, yeah, now I point this, and this, I am going straight against the camera here, right? I'm going straight against you. And now the magnetic field is to this side, but that's easy. That's easy for me to now, what you call, curve, wave my hand to the direction of the magnetic field. Then my thumb gives me the direction of the force. But if I'm coming towards you, and then your magnetic field is this way, and then you will say, hey, professor, why don't you do that? And I say, wait a minute, I may be a very humble professor, but I will not do what I cannot do. But what I can do is now say, yeah, I still go in the same direction towards the camera, but now the magnetic field is over here. And so V cross B, the force is now downward. I just want to, it takes a little practice, I guess, to appreciate. This is what the mathematicians call cross product. This is what they call a cross product, vector product. And the right-hand rule is something. Can we now go on? You have to practice it a little, right? Okay, so let's go on. Okay, so now the book says, after all of this, it's supposed to be, book is not just for biomedical people, but also for engineers. So then they say, hey, what is the technical definition of the magnitude? And I just say, well, I remember this. And then if I put in all the vectors and angles, it is really cross product. V cross B is V sine theta. And don't worry about this. You will not be asked for engineering calculations. What you would need is just the concept. And the unit, okay, now here is where I have a complaint. The unit that the System International, these engineers all around the world have agreed on, is to define the magnetic field in units of Tesla. And in terms of the original Herr Professor Friedrich Gauss, a Tesla is 10 to the 4th Gauss, or 1 Gauss is 10 to the minus 4 Tesla. Since the world accepts Tesla, I looked up Tesla, and that is Nicola Tesla. He is a Serbian-American inventor, was born in Serbia, and then came to the United States when he was, I don't remember how old, but he is an electrical engineer, not a mathematician, not a physicist, but a very good engineer, yes. Mechanical engineer and futurist, best known for his contribution to the design of modern AC electric supply system. And when he was in this country, when he naturalized, he first worked under Edison for a short while. So that's why he knew all about alternating current, generator. And he then went to work for Westinghouse Electric and invented something, a patent, that earned him a considerable amount of money and became the cornerstone. But anyway, so that is Tesla. But of course, today, people don't know who Tesla is. All they care is that there's a car called Tesla, right? That costs, I don't know how much. Okay, so now we come back to this. Oh, this is just to come back to this and get again this right-hand rule. If you can sort of look at the middle diagram, and if you let your thumb be upward and let the four fingers point in the direction of V, it's easy to now wrap it to the direction B, cross into B. And you can say, therefore, now this obeys the right-hand rule. The force is upward, and if it is not exactly 90 degrees, but some angle theta, then this cross product involves a sine of this angle, because it's the component of this velocity that is in this direction that contributes to the force. So that is sine theta. And the book goes through the actual calculation, what's the acceleration, but that's for engineers, don't worry. And now we want to sort of get some conceptual applications. First, supposing we have a electric field, and now I put a charge particle in that electric field. We already know that if this side is positive, that side is negative, namely this side is all positive charge, and then I have a charged particle Q of positive charge, it will undergo a force or acceleration, and it will be forced in the direction of this electric field, so the force is straight. If you have this capacitor turned on, the current will flow straight. And that's due to this formula, F is equal to QE. But for a charged particle in the magnetic field, now, supposing I have the magnet on this side is north, on that side is south, then the magnetic field goes from north to south, right? The magnetic field goes from north to south, but now I have a charged particle coming in on this side now. If I'm coming in on this side, then we have to use the right-hand rule. The magnetic field is this way, and the V is this way, right? You can see if I do my hand this direction, V is this way, and the magnetic field is that way. Therefore, the force is upward. You see it here? The force is upward. And therefore, as my charged particle comes in, it is now being swung around. Are you following? For over here, you had a charged particle coming in V, and then the electric field also caused it to go sideways, but it is going just in this direction. It is in the plane, but this one, it is going out of the plane. The force is upward, so this charged particle coming in now is going up in a circle. I think it would be good to have a real live experiment to show it, but it's very cute in a way. You have a magnetic field, and I send charged particle, something I shoot across. Then what happens is it gets a force that goes around. Unlike here, I don't know if you can appreciate it that easily. It is a charged particle coming in, and now there was a sideways force, so it is horizontal. So it's still in the same plane of this electric field, so it's just going in a horizontal curve. Here, it is going upward. It is being swung upward, so it is not in the same original plane. It is now being swung out of it, and if you follow it, it actually becomes a helical path. It's circling around this magnetic field. And it is due to this vector product. The law of force for a charged particle in a magnetic field is much more sophisticated and complicated than the simple QE, Coulomb law. It is much more subtle. You end up going around the magnetic field. And so now there is a conceptual application of this. And the book gives you an example. Supposing you now have a map where the magnetic field is into the paper. So imagine this X means that it's the end of an arrow. The arrow, the front arrow is a point, but the back of the arrow is an X. And the magnetic field is going into the paper, or the magnetic field is going into this camera. So this is my magnetic field. And my charge is coming in with V this way. So which way would the force be? I have my V this way, and I want the magnetic field to go into the camera. I have my V this way. I want the magnetic field into the camera. Therefore, my thumb gives me the direction of the force. Are you following what I'm showing? Yeah, upward, right? I mean, you should also look at the camera and follow it, right? You say, I see this, magnetic field is straight into the camera. According to my laptop here, this X means that it is straight into the camera, and the charged particle was going in this direction. Then my thumb says it will be going upward. Why? Because it was V this way, and the magnetic field is into the camera. Therefore, the force is upward. And now they say, hey, can you do a certain, what they call a velocity selector? Can you now put a capacitor, put in an external electric field, so as that the force on this thing is unchanged? Namely, it just goes straight through. It does not get kicked out, because this one says the force is, it will now be up and out, bye-bye. They say, can you now put a electric field in here? This was all magnetic field, but can you now put an electric field? And here you now say, what must be the electric field so that my charge goes through undeviated? So that they call this a velocity selector. And now what happens is you now say, I want to have, as this charged particle is coming through, or there was a force upward, I want to put in an electric field such that the force will be downward. Therefore, what you do is you now put in electric field such that it is downward and of just the right strength to cancel this upward force. And you use here. You use this formula here, right? Because you know that this is upward. All you have to do is to make this downward and make the strength E equal to VB, V cross B. So whatever is your B field, you already know your velocity V. You then say there's an upward force. I will now put the electric field negative of that, downward, so that the net force is 0 and my charged particle goes straight through. And this is a velocity selector because it then says that the electric field that I put in had to be dependent on what is the magnitude of the velocity and the magnitude of the magnetic field. And I already know my magnetic field, therefore I have selected a given velocity, meaning that any other velocity oh, it would not be sufficient, and so it will either go up this way or down that way. So this is what they call a velocity selector. I have made it such that for a given V, I know what is my electric field strength I need in order to cancel it, so that the net force on this particular charge of charge Q moving with this particular V would just go straight through. Are you getting better the sense of this V cross B, the right-hand rule? It takes some getting used to, I know, but we will come to something known as Aurora. We will come to something known as Aurora Borealis. And Aurora is basically manifestation of this. So I'm just preparing you for it, because otherwise you say, gee, I'm not an engineer. Why do I need to know all these? But it's for us. Some people would actually pay a lot to go on a cruise to above the, to the north, in order to see this fantastic sight of an aurora. But anyway, okay. The magnetic field always remains perpendicular and is directed towards the center of the circular path. And so now this is the, again, you have magnetic field into the board, and you are going with V. V cross B, when you're down here, the force is upward. But when you come here, because you have been, the force was, this is a centripetal acceleration now. This is centripetal force. So when you come here, you are now tangentially, your velocity is up, but V cross B is still to the left now. So it is still a centripetal force. And so what happens is you end up going in a circle. You see this? Do you see this conclusion that comes from this right-hand rule? Are you able to see this? You have to get used to this notation. You have to get used to this notation. This X means that the magnetic field is into the paper. And first you say, let me look at this guy. He was here. He was first going in a velocity V in this direction, but the magnetic field exerts a force on him. Well, what is the direction of the force? It's V cross B. But B is into the paper, and I therefore know that the force at here, this position, is upward. Somebody had a question. What was the question?
Which direction is the magnetic field?
Oh, it's into the paper. The X means that it's into the paper. You got it? Or into the camera with my laptop here. So the magnetic field is into the paper, and my velocity is to the right on my camera, on my laptop. Velocity V is to the right, and now I need to curve it or cross it. The V into B, and B is into the camera here. Therefore, the force is upward when it's down here. When it came here, the velocity is no longer to the right, but is now upward in my Y direction, the way I have it here. But the magnetic field is still into the board. And now V cross B. V is now upward. B is still into the board, into the paper. Therefore, the force now is sideways. It is centripetal. And when it is up at the top, the velocity now is this direction. And now I have to have my thumb downward. Why? Because V is now in this direction, and I want to cross it into B that is into the camera. Therefore, I have my thumb now is downward. So when it comes up here, the force is still centripetal, It's now downward. That means that it's going in a circle. You got it now? In the presence of a magnetic field, a charged particle coming across it will be trapped in the circle. You got it? When you have a magnetic field, and I am just, I came from somewhere, I have this cosmic ray. There in the cosmos, the sun keeps emitting a lot of these bursts. They call it the solar rays. There are these cosmic rays that come to the earth. But the earth has a magnetic field. So when they come near the earth, the magnetic field traps them. And what do? They then start circling and circling and circling. They have their original motion coming towards us, but now they will be trapped into a spiral. Do you get the rough concept of it? It's a very interesting concept. Yeah? Because I already have magnetic field. Because the earth is a magnet. The earth has magnetic field, even though it is only a third of a Gauss. It's nothing like a Tesla, A Tesla is 10 to the 4th times the strength of a Gauss, but it does not matter. The earth has a magnetic field around us, in a way protecting us. You get the picture now? The earth is protecting us with a magnetic field. And now you have these bursts of cosmic rays, these bursts that come from the sun and come from other stars, because there's a lot of these solar bursts elsewhere, but around near us, it's the sun that sends a lot of these cosmic rays. And when these cosmic rays, they come near the earth, they then say, that is magnetic field. And man, they will be trapped. But they have their original motion, and then on top of it, they'll be trapped into this magnetic field that we have around the earth. And I think, well, this is the, this is just to give the math involved, that there is now a centripetal force on it, and the centripetal force is QVB, because V magnitude, B magnitude, 90 degrees is sine theta is 1, QVB is mv squared over r. Therefore, the radius of this is whatever was the speed of this cosmic ray, the velocity, the magnitude, mv over qb. And so for the Earth's magnetic field, it is a third of a Gauss, and the cosmic ray, the charge is whatever's the charge, is the proton, so that people can know the charge. They know the mass of the proton, and they came from with some velocity. Therefore, there is a certain radius. So it will now be in a spiral. Well, this is just to apply it to a bubble chamber. We don't need to go into this. We already have that. I want to show the oh, don't I have the picture? I thought I had. Gee. Well, all right. Then next time I will download from my other class. Oh, I should have downloaded. Well, okay. There's no time to download. But do you see now? I hope do you see the picture I have? The Earth is a magnet. There's a magnetic field around the Earth. Now you have these solar cosmic rays coming. They get trapped, and now the Earth magnetic field starts and ends. Starts at the South Pole and ends in the North Pole. So all these cosmic rays, for us in the North, they get trapped into this magnetic field, and they will circle around the magnetic field, and they will be going towards the North Pole. Now, as they come in, they have a certain velocity. They will be banging all the atmosphere. They will be banging all the atmosphere, and they will then cause some light emission. Because these protons, they will be banging the oxygens and the ozone and so on, and they will be causing some light, emission of light. And it is the emission of light that you see when you are near the Arctic Circle. When you are near the Arctic Circle, you can actually see what looks like a living fire, and it's usually green. I have seen it. I will share in a little while. I have seen it. It's like a fire from hell. I don't know whether you. Anyway, it's a very eerie experience. E-E-R-I-E. Eerie experience to see the sky, to have a flame, a green flame, and to be alive, because that's what these cosmic rays, they are now circling, plunging towards the Earth's North Pole. And now, for us in New York, it will be very hard to see aurora, the display. Only very rarely, if you're able to go outside New York City, because there's too much light around here. When you go far away from New York City, where the sky is totally dark and black, then on certain days, and NASA will tell you, oh, on this day, because of an extra big solar burst, there can be, Aurora Borealis to be seen even near New York, our latitude. But most of the time, you have to go up to about the Arctic Circle to see it. There was, when I was an undergraduate in Ohio Wesleyan, my math professor, he was interested in astronomy, and then he saw that I was interested in physics. So he says, here, come to the observatory just to see the sky, night sky. So he drove me there. And then after seeing the stars and so on the way back, about 11:30, then in the horizon, there was this green, sort of like a fire, right? And then he says, hey, that's aurora. And I say, wow. So that was the first time I ever saw aurora. And then when you have, enough, you're willing to go on a cruise somewhere up to the north, then people spend money to go near the Arctic Circle to see the aurora. All right, but that's, okay, I think I took too much time on that. Okay, this is now another application of this thing about in a magnetic field that is out of the paper, and this time instead of X it is dot, because the arrow pointing towards you, they represent it as a dot. When you have magnetic field coming out of the paper and you now shoot some what they call ions, I-O-N, when they shoot some charged particle out, when the charged particle comes out, the V is up, right, out, and the B is away from the camera. So then the force on it is to the right. Are you following my hand? With this picture here, I look at the camera, the magnetic field is bumping into my nose. And the ions, these are the charged particles, they are coming up out of the oven here, of the source. So there is this V and there's this B that is towards my nose. Therefore, my thumb gives me the direction of the force, And this means that these ions, these positive charged particles, will now be going on a semicircle. And the semicircle, the radius, depends on the mass of this ion, its velocity v divided by the charge E over B. And clearly, different masses will have different radius. So you can therefore separate out of the ion, and you say, gee, I don't know, my source has all kinds of ions coming out. Some are heavier than others. Well, I can actually now separate them by putting them through a magnetic field, and then at a certain radius, I know these all have to have this little mass m, because the bigger mass, they will now fall outside my detector. So you can therefore measure the mass of these things that come out, and you can say, oh, I have identified that out of the source, it is alpha particle, it is beta particle, and so on. And that's what people do, engineers and scientists, they do, because they have radioactive source. If you have radioactive source, for a while, people didn't understand what was the radioactive things that are coming out. And then they discover, whoa, that indeed there are these so-called alpha particles, and the alpha particles have positive charge, and their mass is the alpha particle mass, which is, I forget the mass, it's either twice or 4 times the proton mass. So they have measured it by this. And now we don't need to do this. Okay, now here we're beginning to come to another aspect of this force law, magnetic force. You have a loop. You see, this is a loop, and the loop has been shaped exactly as a loop. And this loop will have the way they have it, the current flowing this way up and then go back to the source and come back down. So they made this loop such that over here, the current is flowing the way it is given, right? And they have put this loop within a magnetic field such that the magnetic field is downward. Okay, you see it? So now we need to now say, gee, which way is the force now? I have V, because the current is V, QV, and the magnetic field is downward. Therefore, I cannot use my thumb. I got to now do it this way. I have V cross, yeah. I got to now write it this way, right? I have V, I have to put my G. How do I do that? I have my V and my B. V and my B. Here. V and my B. V is this way, and B is downward. And so, of course, my force is in the direction they have given. Do you follow what I'm doing? I use my own V cross B. My V is pointing this way, and in order for there to be a V cross B, and since B is downward, then my thumb has to be pointing in this direction. Why did they arrange it this way? Because they want the magnetic field to actually now force this loop to go upward. They want the magnetic field to force this loop to go upward, so that indeed you now force this circuit, the loop, to now respond to the magnetic field by going upward. Later, we will then look at the opposite. The opposite is I actually have a magnetic field and I purposely turn it. I purposely turn it, you know, because I have my hydroelectric plant and I have my things arranged so that I have a loop, and I purposely turn it. And then when I turn it, the current that is induced will flow in a certain direction, which we will learn to be the Faraday's law. And then as it is going up this way, the current flows in this direction. But when it is the other side, you know, because this is a loop this way, when it's now the other side, then the current flips around. Why? Because my magnetic field is still this direction, but now you're flipping it around, and that's why you get an AC current. We will come to that aspect of it when we come to the chapter on Faraday's law. But here is just simply the first such application where you purposely make a loop, a rectangular loop, and then have fun with it, because the magnetic field will now, when you have a magnetic field and you turn on the current, it now is moved. It flips. Is this okay with you? Yeah, I mean, you have to you have to play with it, but this is now where you actually have some fun with it, because you purposely make this, and before you turn on, it just hung down there, no big deal. You have magnetic field, but it didn't do anything. But you turn on the current, whoop, it moves. And this is where, again, they go through the calculation, where you have your current and you have your, yeah, somebody, yeah, no, that's a good observation. If you were to flip the current, then it turns the other way. In other words, this would be one way of you to sort of play game with it and say, hey, I want to now first flip it this way, and then I turn the current and it will flip the other way. So it can go flip, flop, and you can have some fun with it. Was that what somebody had asked for? Yeah, okay. And now this is just to express it in terms of the mechanical aspect of it. If this is the force law, you want to re-express it in terms of a current. So then you say, gee, I have now Q, but I have a string of Qs in a given time interval. So that would be delta Q over delta T. And then I will now say V delta T. Well, that's the time, the distance, the length of the wire, basically, because I have a current flowing this length of the wire. So that's L. And so I can re-express this force law in terms of an application. You have a current and you have a wire, and the wire carries a current I, and it is of length L. Then if this is the magnetic field, strength of the magnetic field, the force on this wire now, the force on this wire is ILB sine theta. They all came from here. The fundamental thing is that the force law is very subtle. And because the force law is so subtle, you can now have things that cause things to go in a spiral, or all you did was you had a wire of a certain length carrying a certain current, and then in the presence of magnetic field, oh, there's a force now, and the force is upward. So all of a sudden, your wire now starts going upward because you have a current flowing through it. When you did not have a current, it just stayed there. But because you have a current, it goes up. And now if you reverse the direction of the current, it comes down. So you can have a tick-tock, TikTok if you want to play with it. All right. Well, now maybe I will stop here because this comes to the engineering aspects of applications. Yeah, maybe I will stop here. Ask any questions. You can. I wish I had downloaded my thing on the Aurora. Next time I will show you the Aurora. And maybe show you a little video of the Aurora because it's very impressive. And then you can understand. Then you can understand how this Earth really protects us. It really takes care of us. Okay, now the question is, how many questions will be on the exam? I think it will be like 15 questions. And as I kept telling everybody, it's one where I have allotted 5 minutes per question for you to, work through the multiple choice. And they are sort of similar. I cannot say I get it from Wiley Plus. They are sort of similar, but they involve sort of simple concepts. When you do the Wiley Plus, then you are basically practicing for the exam. All right. So do make sure that you go over the Wiley Plus, and it would help to, even though it's past due, it's available so you can look at it. But I will not be saying, oh, I will pick homework 15 or 17 or 18, number 6 to be in the exam. I don't do things like that. I may take the concept and then ask a slightly different one. The same concept, but a slightly different one. So what you need to do is to just look at it, stare at it, don't plunge right away into it, but think as to what is involved, read the question carefully, and then answer it. And next time, I think certainly by October 4, I will have already a good solid of the test, and then we can have a preview. No, not preview, not review. I guess preview, sort of summary on what you might want to be prepared for. Okay.
Professor,
Any?
are they all multiple choice or like short?
There will be some that are calculated formula, some which will be multiple answer, which is really multiple choice.
Professor, are we gonna be able to see all the questions in one sheet? Or like,
No.
so it's gonna
No,
be
it's
one question and then we go into the next one.
that's
Can,
right.
can
That's
we
right.
go back or no?
No
No, okay.
backtracking.
Okay, no
Yeah.
backtrack.
Yeah.
Thank you.
Okay.
Do have like multiple attempts, right?
What?
We do have like
Yeah, 2
multiple
attempts. You have up to 2 attempts, and then it will be graded on your highest score on the attempts. But just be careful. Each attempt is itself randomized. So even if it was question number 5 on the first attempt, it may be question number 12 on the second attempt. So it's just that you can keep a note of whatever it is you did. And then you'll be able to say, oh yes, I know what I did, since you have your own laptop, computer.
Thank you.
Any other questions? The 2 attempts are given, yes, within the hour of an hour and 15 minutes, right? Oh, calculators are allowed, right? But the fussy thing is, you got to remember, if the question says, give me the answer to 3 significant figures, and then you give an answer that is accurate to 5 significant figures, Blackboard will say, wrong. And what I'm going to ask the grader to do is, if what you have is actually correct to within 3 significant figures, it's just that you were not so careful in looking at the wording, oh, then you will get maybe instead of 10 points, maybe 7 points, huh? Or 8 points. You get partial credit. So the grader's duty is to look over your answers and assign partial credit. All right. Otherwise, Blackboard will just say wrong, wrong, wrong. Even though you are not really that wrong, it's just that you, because Blackboard is very fussy. Any other questions? Oh, I better